All right, good morning, everyone. So I guess today we have our last in-person meeting, and we're going to be talking about a very popular algorithm, random forest, and also implementing that using tidymodels in R. So I sent an email earlier this morning asking for you to do all the setup with a new project that is called, I believe, 13 or 12 RF. 13 RF. So if you have not done that yet, please do that in the next moment here. All right, if you have already done it, then I ask that you launch that RStudio project side. And then we're going to launch that partial script. So I asked you to move the partial script that I shared on GitHub to the code folder, and also moving the same data set that we've been using for the previous exercises to your data folder. So we're going to be using the same data as well. All right. Okay, so for today, our goals of this exercise is going to be to understand how a random forest algorithm works. It's going to be a different type of, well, it is a different model, and it's really interesting to really understand how random forest is working behind the scenes, because that is going to be what makes it one of the most powerful yet simple machine learning algorithms, and a very popular one because of that. And then we're just going to use the same workflow that we used the two previous times to train our random forest model. And then just go through the pre-processing, training, evaluating, just like before. So these steps will always be there for any machine learning algorithm. And I want to bring beyond the algorithm itself, I want to bring one new topic compared to the previous ones, which is going to be selecting the best model using a different approach. So if you remember, when we did this exercise with ElasticNet, we selected just the best model overall. When we did this with conditional inference tree, we selected the best model within one standard deviation of a given metric. So either RMSE or R square of the best model. What that does to help us is, again, if your best model is a very complex model, and the second best model, so number 2 in the list, is very close in performance, is lower but close in performance, but it's a lot simpler model. Using these approaches help you to select a model that may give you a little bit less predictability, but a lot simpler, which sometimes that trade-off is there. We have to think of it. So today, I'm going to be introducing, instead of within one standard deviation or a standard error of a metric, it's going to be within a given percent loss of that metric. And when we get there, we're going to talk more about it. But introducing you another new aspect of this as well. Okay, so this intro here is basically the same, right? So we have multivariate data sets, which potentially have multicollinearity issues. We want to handle that somehow. So either through dimensionality reduction, like with PCA, or doing variable selection. Today, we're going to use a model, again, random forest, that doesn't necessarily do variable selection, but it handles multicollinearity behind the scenes in a way that none of the others did. And we're going to talk about that in a second here. All right, so random forest is one of the most popular algorithms for a reason. It is supervised, and I guess I did not explicitly mention this on the previous two algorithms, but ElasticNet and conditional inference tree were also supervised algorithms. You know that because you're providing a Y variable. If you're providing a Y variable, it is supervised. You're given the labels, you're giving the number you're looking for and seeing what impacts that number. So these algorithms are all supervised. And random forest is often referred to a very good algorithm out of the box or off the shelf, meaning that even though it has hyperparameters that you can fine tune, but just the predictive ability of the model using the default values is already pretty good, right off the shelf. Of course, we can further improve that, but it already comes with hyperparameters that can do a very good job without being tuned, which is not the case of the other models, right? The other models, they really require you to look deeper and find specific hyperparameters for it to perform well, even the first time. So one thing, or a couple of things that make random forest different and that gives it its power is based on two random processes that it runs behind the scenes when it's training a model. The first one is called bootstrap aggregating, or for short, people also refer to this as bagging. So you may see this term in the literature or in blogs or whatever you're reading. So it does a bootstrap aggregation on the rows. So we're going to talk about that in more detail in a second. And the second process that makes it very powerful is that it has a random selection of a subset of variables at each split. So two random components here, one being applied to, so if you think of our data set with 600, well, I guess on the training set, how many rows we had there? I don't remember now, 400 some, I guess. So almost 500, let's say we have 500 rows, right? So the first thing that makes it powerful is that's gonna take a bootstrap sample of those 500 rows. If just to recall, we talked about bootstrapping already. What bootstrap does is it takes your 500 rows and is going to generate another copy of our data that has the same size, 500 rows. However, it's doing this at random without replacement. What that means is you will be able to get the same data, the same original data point appearing more than once in your bootstrap sample. But then you do another bootstrap sample, and then other original samples may appear more than once in the other bootstrap sample, and so on. So each bootstrap sample is going to have the same number of rows as the data that's being based on. So if your data has 500 rows, each bootstrap sample is going to have 500 rows, but different observations from the original data set could appear repeatedly in each one of the bootstrap samples. So maybe, you know, a site in Texas in 2018 might appear the same site, the same row might appear 3 or 4 times in your bootstrap sample, whereas on your original sample appears only once. So that's what bootstrap is doing for us. And when we're training a random forest algorithm, it is doing that. It's taking bootstrap samples, meaning the same number of rows, but any given observation could appear more than once on the sample. So it has that randomness to it. And if you think of it, if I have 500 rows in my original set, if each bootstrap sample has also 500 rows, and if any observation could appear more than once on my bootstrap sample, it also means that you may be leaving out some of observations from the original that are not being sampled on a given bootstrap sample. If you perform many bootstrap samples, most likely all observations are going to be appearing across all of them, but they may be missing from some of the bootstrap samples, and some of them may be appearing more than once. So that's that randomness that bootstrapping does for us. Is used in random forest is one of the reasons why it's such a strong algorithm. The other part of that is a random selection of a subset of variables. So bootstrap samples happen at the row level. Random selection of columns of variables happens at the column level. So when you're building each one of the trees in a random forest, you're going to be for each node of that tree. So think of a node as we saw the last class, right? So you have a node that breaks and then each node breaks. So each node here, random forest is only evaluating a random subset of columns. So not all weather variables would be evaluated at each one of the nodes that you can split. It's going to be only a subset of those columns, a random subset of those columns at each split in each tree. And then the thing about random forest is it's a forest. Then the reason why it's a forest is because it's a collection, it's an ensemble of many individual trees, right? So each tree here has that random component of being trained on a different bootstrap sample And then each node of the individual trees, it is only evaluating a random subset of columns. So those are the two random processes that goes on, or that go on a random forest machine learning algorithm that makes it very powerful. So if we just talk a little bit in more detail about each one of these strategies, so bootstrap, aggregating, or bagging. I guess I only explained to you the bootstrap side of it. I have not told you why it's called aggregating yet. But again, let's say if we're training 1,000 trees in this forest, each tree is going to get a bootstrap sample of my original training set, right? So that incoming training set for each tree is different for each one of the trees because it's a random bootstrap sample. And as you have many trees, each tree being trained on a slightly different data set, that gives you that variability. And then the reason why it's called bagging is we're going to see this in more detail in the next part here of the script, is because now imagine that you have each tree being trained. You train 1,000 trees. How do you make a prediction? Your prediction now is going to be made. So let's say I give a new data point from my test, right? That my trained model has not seen yet. I give this just the X variables to the model, and it's going to spit me out one prediction. How is it giving me one prediction if I train 1,000 trees? Well, that's where the bagging part comes from. So you're training each individual tree, and imagine you give a test sample. Each tree is going to give you a different prediction value. So let's say strength, right? You're going to get 1,000 prediction values for strength for that one observation you're giving to predict. What bagging does is then basically averages all of those 1,000 predictions to give you one. So it gives you one prediction back. That's the average of all the 1,000 trees you had in this forest. If it is a regression approach, it does an average of all of the trees. If your Y variable is categorical and you're doing classification, which is not what we're doing here, then your tree is going to give you a vote. So let's say each one, or I'm sorry, your trees are going to give you a vote of like, well, I think this observation will be classified as high strength. And the next tree says, I think it's medium strength. I think it's low strength. But it does this across all 1,000 trees. So it gives you a vote. What was the class that was most voted to classify as high, low, or medium strength? And that is the prediction of the forest. So that's where the bagging part comes into play, because it is aggregating over an ensemble of trees. And random forest is an ensemble type of model. In that sense, that is creating many models and giving you the average or most common, average in the case of regression, most common in the case of classification, prediction across all the trees in the forest. All right, so we just talked about bootstrap aggregating or bagging. Again, the bootstrap comes from taking a bootstrap sample of your data for each tree to be trained. So each tree is seeing a slightly different version of your data. And then aggregating in the end to give you one prediction across all the trees. The other random component here of random forest that makes it very strong and reliable algorithm is the random subset of features. So if you think about it on the conditional inference tree model, at each node, the algorithm was seeing all the variables and running by very relationships between strength and each one of the weather variables and selecting the one that had the highest p-value for it to be the variable at that split. In random forest, it is actually not looking at all variables, and it is not selecting the same way either. So it's looking at a subset of those variables. Normally, for regression, the subset that each node sees is the number of features divided by 3. So for example, if we have, I think we have 72 features, if I remember well. So if we divide 72 by 3, then it means that only 24 random columns from our data set are being evaluated at each node of each tree. So if we have 1,000 trees, at least 1,000 different random selections of variable, but probably more because each tree may grow more than just one breakpoint. So each node of each tree in this forest is only going to be seen by default. This is the default value of this parameter. Is only going to be seen as a random subset of 24 columns. And this here is another thing that helps random forests to be a very powerful algorithm. Because if you think of it, if you're giving every time the same variables, you may be creating very similar trees. So if you have 1,000 trees and all trees are seeing the same rows of data, the same columns of data, then maybe all of them are going to be very similar. That's not the goal here. The goal is to create trees that each individual tree is based on a different version of your data and is able to create a different tree overall, perhaps using different variables. Actually using different variables at each one of the splits, and also seeing a slightly different version of your rows because of Bootstrap. So in the end, your trees may be very diverse. So one tree has completely different variables that it is using to make a prediction than the other. But overall, your idea is that when you take the average of all these trees, you get a very robust prediction because they are variable and they were able to look into different aspects or sides of your data, I guess. So this argument here of how many columns, how many features, how many variables each split in each tree sees is called mtry. And again, the default value, if you're doing regression, which is what we're doing, is p divided by 3. So our p here is number of features, 72 divided by 3, which is our case. But if you're doing classification, it is the square root of p. So we're not doing classification, we're using p divided by, or the algorithm is doing p divided by 3 as the default value. And again, because you have these two random processes going on at the same time, random forest then becomes a very strong algorithm because it creates a diverse set of trees, and which tends to lessen the tree correlation, which helps us to increase our predictive ability or predictive power of this algorithm. One thing to think of is, I think we mentioned this briefly when we talked about conditional inference tree the last time. So even though the way that a random forest tree develops is different from how the conditional inference tree develops, that you're using slightly different algorithms and ways to do that. But the conditional inference tree, we get one tree in the end, which is great if you want to interpret it. However, that tree is it has high variance, meaning that if I train that model with one set of data, and then I fully train it doing the proper framework that we're doing here. But if you get a slightly different training set, you may get a different result. That means that it has high variance, right? It's creating a best model that is different across different versions of our data. That algorithm has high variance. In the case of random forest, what it does is your individual trees have high variance. So they can be completely different from each other, and we want that. So individual trees in random forest have high variance, but that is taken care of when you bag them. When you aggregate all of their predictions into one average value, then you decrease that variance and you give a prediction that's more stable. So again, that's the power of random forest comes from that. So one thing I want to tell you, and I hope that this is a strong takeaway from the machine learning part of this course is, we're going to stop here with random forest. I'm not going to be able to show you other algorithms, but some of the other common algorithms people would learn in a machine learning course would be support vector machine, gradient boosting, which is also an ensemble model that is in ensembling is similar to random forest, but does that differently, and really many other algorithms. The key takeaway I want you to have from here is, even though we're not going to cover this in class, once you learn this workflow, you need to do two things if you want to learn any of these algorithms. One is to understand what the algorithm is doing, like we're doing in the introduction of all of these courses or all of these lectures here. And then identify which hyperparameters there are in that algorithm and which ones are important for you to tune. Those two things you're gonna be able to run any algorithm with this workflow. Because as you're going to also realize from today, we're just going to be changing very few things in this code to make it run random forest as compared to how this code looked like when we did CIT last Tuesday. So again, if you can identify the algorithm, understand how it works, and understand which hyperparameters you can fine tune for that algorithm, that's all you need to know to then learn on your own after this class. In the case of random forest, I want to bring to you three main hyperparameters that we're going to fine tune. So one of them is going to be the number of trees in the forest. So there is a default value that if you don't specify anything, I think the default is 500. So it will at least give you 500 trees by default, but this number can be fine-tuned, and we're going to see the impact of that on performance. And then the number of features randomly selected at each split of each tree, which is called mtry. So I guess the name is very explicative by itself. It's just how many features you want to allow it. So it has a default of p divided by 3. In our case, that would be about 24 features, but it could be less, it could be more, and there are going to be implications if you do more or less as well. And so number of trees in the forest. Let's talk about a couple of scales that these hyperparameters have. So the number of trees in the forest has nothing to do with how an individual tree is growing. It's just telling the algorithm how many total trees you can grow, right? So it controls the size of the forest, if we think of that. Now, the number of features randomly selected at each split is also not really controlling the size of the individual tree. It's just, giving a different version of the data for that split to look at. But that by itself does not control the size of the tree. This third hyperparameter here, which is the minimum node size, is the one that actually controls how small or large each individual tree can be. So the minimum node size is going to be the minimum number of observations that a node has to have for it to be allowed to break down into further nodes. So let's say if this number here is small, so let's say 5, each node that has at least 5 observations is going to be allowed to break down until the bottom ones have 5 or less. If node size is a larger number, so let's say 50, it means that a node will only be allowed to break further if it has at least 50 observations. So this here is in a random forest it's not the only one controlling individual tree size, but it is one of the most important ones controlling individual tree size, which is different from our conditional inference tree. How were we controlling the size of our conditional inference tree? Say that again? The depth, right? So the depth was one. So depth and node size are related, but not the same thing, right? So I could have more depths, less depths, and have varying node sizes across those, right? So they're related, but not the same thing. So depth was one of them. Can someone else help me with the second one? So we had the minimum criterion or the p-value of the relationship of strength and any given weather variable. So if that p-value was greater than our minimum criterion, then, so let's say if you get to one node and you do all your strength by each one of the weather variables, and at that subset of the data, no variable is able to create a p-value that is less than 0.05, then this node does not break. It does not select any variable to break, right? So in CIT, it was the depth and the p-value or minimum criterion. Here in random forest is the size of each node. That's what's going to determine the size of the individual trees. So I just want you to think about here because, of these 3 main hyperparameters that we're going to control on random forest, one of them controls the size of the forest itself, which is the number of trees. One of them does not really control the size of the forest or the tree. It's just creating variability on each tree, right? Is what columns are being seen in each split. And the last one here controls how complex each individual tree can be. So one controls forest size, one does not control either forest or tree, and the other one controls tree size, individual tree size in the forest. All right, so let's talk about here about each one of these. So we have a better understanding of how changing these hyperparameter values will impact performance of your model. When it comes to number of trees, so normally we just want to have a number of trees that minimizes the error, but we don't have to go beyond that point anymore. At least now for predictive performance. A good rule of thumb is to start with 10 times the number of features. So if we have 72 features, we would do a tree forest size that has 720 trees in it. And then the number is going to fluctuate lower and higher as well. So this is it's not from our data, it's just an example from another source, where if you have very few trees, so a forest that has, I don't know, let's say here 10 or 50 trees, it has a very high error rate. So our MSC is very high. And as you start increasing the number of trees, you're decreasing the error until a plateau point, right? So maybe for this example here, if you would be between, I don't know, it doesn't seem like you gain too much more after 250 trees or so. So we have, if you have many more trees than what you need, it's not really gonna hurt you when it comes to predictive ability. It's just gonna take longer to train the model, right? So if I needed, I don't know, 250 trees and I'm training with 1,000, I'm using more computational resources, which depending on the size of your data, that can be a restriction. So that's where the number of trees come into play. You wanna have sufficient number of trees to decrease your error, but after a certain point, you're not gaining much more on predictive ability, and you are just consuming computational power at that point. So more trees will provide more robust and stable error, and also variable importance measures, which we haven't talked about yet, but we will. However, as you increase the number of trees, you increase your computational time and resources with that. All right, let's talk about the next one, which was mtry. Again, that's how many random columns you want to allow each split to evaluate, or each node to evaluate. So this number here is going to help us to balance low tree correlation with reasonable predictive strength. So the thing here is if you have very few relevant predictors, so let's say that in our data, out of our 72 features, let's say we only had 3 of them that were really good predictors of strength. The others were just noise. They're not very good at predicting. So if we have very fewer relevant predictors, a higher value of mtry could be better. The reason for that is imagine if in our 72 features, only 3 of them are good predictors. If I have a value of mtry that's very restrictive, let's say 10, the chance of those 3 columns that are very important in predicting strength falling in a sample of 10 out of 72 is small. So if I increase mtry to, let's say, 50, now 50 out of 72 of my columns are being sampled at each split. There's a higher chance that these 3 very important variables would be within that sample of 50. So if you have, again, fewer relevant predictors in your data or very noisy data, a higher value of mtry tends to perform better because it is more likely that one of those few relevant features will be present at each subsample of your columns at each node split. On the flip side of that, if you do have many relevant predictors, so not only 3, let's say that, I don't know, 40 out of our 72 predictors are very good predictors of fiber strength, then a smaller, lower value of mtry might perform better, right? Because then it's more likely that in each subset of columns at each node split, one of those 40 will be present and will be able to give you a good tree. So this is just an similar example of the one above, but now each line here is a different number of mtry. So what we see here, if M trie is equal to 2, which is the top curve here. Then our error, we decrease the error as we increase number of trees, but even when we reach that threshold, that error level or the threshold is still higher from other M trie values, right? So an M trie of 2 means that only 2 random columns are being evaluated at each node split of each tree. Now, each one of these lines here have a different number, and that's the M trie number. So we see that this line, the pink line is M trie equals to 80, then the blue is 60, then the others here are 41, 26, and 21. Really, 21 here seems to be the sweet spot because it's the one that is at the lowest error rate, right? So as you increase number of tree for all of these M trie values, you decrease the error until a point, and then M trie of 2 has the highest error overall. M trie of 21 has the lowest value overall. So this M trie, again, is important for us to fine tune to understand which value we need in our data sets. And then lastly, of the 3 is node size. So again, node size is going to be the minimum number of observations in each tree, each node of each tree, how many observations it has to have for it to be allowed to further break down into other splits. As we already talked about, larger values of this hyperparameter, so let's say 50, would be more restrictive, would create shorter trees. A lower node size value is going to be less restrictive, is going to allow your tree to break down, each individual tree to break down further and have a deeper tree. If computational time is a concern, you can often decrease the runtime substantially by increasing the node size and only having marginal impacts on your error estimate. So of the 3 here, really the first 2 are the most important ones, the number of trees and M trie. Node size is going to have a secondary, it's going to be a secondary hyperparameter impacting your error. It will impact it, but not by the same magnitude as number of trees and M trie. So here's an example where you have the how much your error rate is increasing and how much on the y-axis and how much your minimum node size is increasing. So a low minimum node size creates a very complex, deep tree. A higher node size creates a shorter, simpler tree. So we see here that the change in error, even though this curve here looks kind of dramatic, but if you look on the y-axis values, the change here is going from 0 to 3%. So you're changing your error, maximum increasing it to 3% in this example, but really the main impact is on runtime or computational demand. So as you increase node size on the x-axis, on the y-axis of the second plot, we have reduction in runtime, which is going from -10 to -50%. So let's say if a given random forest algorithm is taking 2 hours to train for some reason, if you have a very large data set, then changing node size can reduce that in up to 50%. Well, I guess up to 50% in this example doesn't necessarily translate to every data, but this is just one example where here you're losing only 3% on error, but improving runtime in up to 50%. So node size helps you with that. All right, I know we talked about some of these points already, but I do want to be repetitive here because I think that may help you to grasp the concepts a little bit better. So so again, a random forest is called a forest because it has many trees, right? And we train each tree individually in this forest. So how do we grow each individual tree here? So basically, that tree is going to grow based on the node size that you're allowing it to have, the bootstrap sample of the data that you're giving each one of those trees, which is different for each tree, and then evaluating a given number of random columns at each split. So I'm thinking of one tree only here. This tree is seeing a bootstrap sample of my data, starting on the top. At the first split is going to randomly select, so let's say 20 columns out of my 72. within those columns is going to make a decision of which one of those columns is the best and what break is going to use. We're going to talk about this in a second, how that works. And then it's going to break into two nodes. These new two nodes, if they have more observations than your minimum node size, then they are going to evaluate a new set of random columns again. So new 20 variables here, new 20 variables here, and then further breakdown until we reach your minimum node size. So just, to call this again, each tree has a bootstrap sample of your data, and then each node from that bootstrap sample that has all the columns, but just is impacting the rows, the bootstrap impacts the rows, each split is going to be evaluating a random subset of columns, right? So it's not like a random subset of columns for the whole tree. No, it's a random subset of columns for each split in that tree, right? So just to make that clear. All right, so then how does, let's see if I can make this, no. So how does, trying to make these plots a little bit bigger. Not sure if that's working, but. Okay, so how does each tree then selects what variable of these, let's say, of the 20 random columns or variables at each split? How does that split decides which one of the 20 is going to use and then what breakpoint is going to do? It's basically by random chance. So here we're seeing that process happen. Imagine one tree, one node, and it's considering, let's say, 20 variables. I'm showing you here what happens for one of those 20 variables. So basically we have each plot is a random split of that variable, where you see, so the data behind is the same, but is doing a random breakpoint on this single variable here. So each plot is the same variable, it's just changing where that red line that represents the breakpoint is. So we randomly choose a breakpoint here, calculates the error. If it breaks there, what would be the residual error of the two parts? And then it takes another random breakpoint. If it breaks there, what would be the residual of those two remaining sides? And it does that many times. And this is just the process for one of your 20 variables. It's going to do this for all of your 20 variables. And in the end, it's going to choose whatever variable and whatever breakpoint was able to reduce the error the most, which is a different way than conditional inference tree. Conditional inference tree does not do this just by random chance, right? So if you remember, conditional inference tree first runs a bivariate relationship of your y variable with each individual x, selects the model that has the lowest p-value, and then only on that x variable that was selected, then it does a binary split search. So a different approach between how random forest and conditional inference trees do it. Now let me decrease the size here. So this figure above, again, is just is showing this process of finding a breakpoint for one of the variables, but it's going to do this for all of the variables evaluated at that split. And then in the end, it just chooses the one that has that decreases the error of the breakpoint the most. All right, so that's how one individual tree grows. Now, how do we go from trees to a forest, right? So this, again, random forest is an ensemble algorithm of many trees, where each individual tree is going to be made up from a bootstrap sample of original data, and at each split, a random sample of the columns of that bootstrap sample of the data. Then this forest is going to grow by growing many individual trees. And when you're making a prediction, each tree makes its own prediction. So we talked about this already. Each tree is going to be able to give you one predicted value. And in the end, this is going to be bagged, it's going to be aggregated. And in our case, it's going to be an average of the prediction of all trees in the forest because we have a continuous variable. So the forest itself in the end gives you one predicted value, even though that one predicted value was aggregated over many individual trees in the forest. All right, so I have, again, some pros and cons of random forest. These are not extensive pros and cons, are some of the ones that I guess I came across. So very good performance, even without tuning, which is not common for other algorithms. It is very simple to train. It can also model nonlinear relationships because it has that tree structure in it, even though it's a forest. Can be used with both numerical and categorical response variables. We're just seeing a numerical one, but it could be categorical as well. It handles NAs. Some algorithms do not handle NAs. If you remember, PCA does not handle NA. K-means does not handle NA. So here, conditional inference tree and random forest do handle NAs and offers this great balance between variance. So it has high variance because it grows many trees that each individual tree is probably overfitting. It's probably too complex. However, because it averages them in the end, it reduces that variance and brings more bias into the equation. So it has a good balance between variance and bias because of the way it is trained. Some of the cons of random forest, and really, this is again not an extensive list, but more from the way I've used it, it's just that it's not as interpretable, right? Because imagine with a conditional inference tree, we had one tree model that we could look into and interpret. With random forest, you may have 1,000 trees. How do you show 1,000 trees? You don't, right? We don't do that with random forest. It starts getting into a little bit of the black box types of models, even though it's not the most black box type of model, but it starts getting into that because now your prediction, again, is the average across many models, many trees in this forest. So it is not as easily interpretable as a conditional inference tree. However, is also not the worst. We're going to see, we can look at variable importance. That gives us some indication of how different variables are related or are impacting your model, but it still is not like a coefficient you can look into and say, oh yeah, I understand that as this variable increases, fiber strength increases as well. It's not like that. All right, so we got through this first introduction here, which was important. Now let's get to the coding side. I believe, so I left you here, the one difference that you did not have before is this package called Ranger. This is going to be the engine that we're going to use to train a random forest model. I don't think you have it from previous package dependencies. So go ahead and install it. And then after you do that, just run this chunk. And I think this is the only one that you needed. I'm not 100% sure because I already had these packages installed. So if it gets to a point of the code that you see works on my side and it does not work on yours because it says function not found, let me know. We can look into that because it's probably, maybe there was another package that I didn't realize that you needed. All right, so go ahead and read in the data. Again, same data set as we've been using for the last exercises. So 698 rows, 75 columns on the total data set. Again, I want to call the attention here that I left you a lot of the code because it was the code that we already did before and did not change. So again, I want you to notice and be aware of how much code we're not going to have to rerun, meaning that we have already done it, meaning that it's code that we're just recycling over these different models. So a same workflow, just changing a few things is going to work for any model. So we're setting the seed here, getting our initial split with the 70-30%, 70% on training, 30% on testing. The next split or the next chunk is going to be to pull the training data out of that split. The next chunk is going to be to pull the testing data. So again, our training data has 488 rows. This is what we're going to use to fine tune the hyperparameters. Our test data has 210. We're not going to see this test data until the end. Remember, that's the one we use for predictive ability to measure predictive ability of a model. So we do not want this data to leak into the training process. We're going to do some data processing as well. by creating a recipe, just like before. You can just get to the chunk. So again, random forest, we don't need to normalize the variables. I guess if you wanted, you could do that because that wouldn't necessarily impact your, because, okay, let me just talk briefly about this. For elastic net, we needed to normalize our variables because we did not want a variable that has a large range of values to have a higher impact or a higher coefficient than a variable that has a lower range of values. So by normalizing, we would put them in the same footing. They're comparable, right? Now, for conditional inference tree, that was not a problem because there was no part of the model that more than one variable was evaluated together. They're all evaluated separately and then choosing the best. Now, in random forest, I guess you could normalize if you wanted, you don't have to. But if you decide to normalize, you could do it because you're not gonna lose in interpretability. On conditional inference tree, you do lose in interpretability if you normalize, because the tree is the breakpoints of the tree, if it is normalized, is gonna be like rainfall greater than minus 0.2. Makes no sense because it's on a normalized scale. For conditional inference tree, normalizing makes it less interpretable. For random forest, that's not the case because we're not going to be looking at those values anyways. In the end, you're going to see that we're going to look at variable importance, which the scale of that is not really interpretable as far as the coefficients. So we don't have to normalize, but if you wanted, you could do it. So I'm leaving you here the same recipe as from the previous exercise where we define our formula and the data. And then we're just removing year, site, and then any variable that has the months of January, February, March, April, November, or December, as we're assuming that those are outside of the growing season, they should not impact what goes on in the growing season, which is what we're looking into as far as cotton fiber strength. So make sure you run this recipe. We're going to prep this recipe, so basically making it be applied to our data. And now we finished with the pre-processing. As you notice, there was no difference in the pre-processing from what we did today and what we did for conditional inference tree. Now we get into the training part of it, where we're going to specify the model, the engine, and the hyperparameters. Yes?
I have a question regarding the pre-processing. If we would have categories of variables, do we need to turn them into dummy variables to be able to enter into the model, or just straight from them?
Okay, so that's a great question. We don't, but it depends on the model itself, right? So random forest. So let me just come back here on the recipe side. So I left you a link here that if you want to look more into what options you have for different recipe steps, I just want to show you some of that. So there's going to be a lot of different steps. Some of them, for example, something we did not talk about in this class is if you have an ACE, you can impute them. We are not doing that, but you could use there are some steps for imputation if you have A values. Was that work? Wait, I think it's working now. All right. So there are many steps that we can include here on the recipe. And one of them is dummy variables and encodings. So what Jonathan is asking is, if you have a categorical variable, can you have a column saying, let's say, soil type, and then having 10 different soil types listed? Or do you have to create some type of encoding? I'm not going to talk a lot about this. So if you have not seen in the past, this may not be sufficient for you to fully understand. But the first time, at least, that I saw this was in regression. So if you're doing regression, you can create dummy variables, all of your categorical variables on the X side of the formula. So if you create dummy variables, it basically means that, let's see here. Or maybe I can pull out an Excel so people online can see. So if you have a column that, let's say, soil type, that it has soil A, B, and C. If you create dummy variables out of this, instead of having a column saying soil type, this would translate into having columns A and B pretty much. So if a given observation in your data set had a soil type of A, that is coded as 1, and then 0 and 0 for other soil types. If that row had a B soil type, then you get a 1 on the B column and zeros elsewhere. And if you have all zeros, this basically means that is C. So you don't even have to specify, is implied. So this is dummy encoding or dummy coding in statistics overall. There's another type of encoding which is called one-hot encoding, which the only difference, so if you're doing dummy encoding, you don't get the C column. This is implied. So this would be dummy encoding. If you're doing one-hot encoding, you would have a C that would just have a 1 whenever the level of soil for that observation is C. Again, if this is the first time you're finding this is not a comprehensive explanation. I don't expect you to understand. But yes, you can do that here easily on the recipe. So there is a recipe step that you can, so there's a step dummy, there's a step one-hot as well. Let's see. I know there is a one-hot, maybe it's just not named that way, but there are many different steps of processing you can do here. So another one that we didn't talk about is you could do a step PCA right on the recipe, which basically does a PCA for you and gives you back, I think, the first 4 or 5 PCs by default. So there's a lot of steps you can do here to process data. So I would recommend you take a look at this. But yeah, so, and I guess coming back to your question, if we have to do some type of encoding or not on categorical variables, we don't, because random forests do not require that. Some algorithms will require. So it's an algorithm dependent option, I guess. So I know here, let me also show you another. So towards the end of this exercise, I have another resource, I have another chunk here, or I have another session that is further resources, which is where I get a lot of this material from. So one of them is called Tidy Modeling with R. And in there, they have a list of engines, algorithms, and processing steps required. So it gives some examples here like dummy or zero variance values, imputation, decorrelation, normalizing, or transform. And they have each one of the model types and what is required. So you can also look into this to see what is needed, including if you need to do any dummy processing with them. All right. So let me see where we were. We were on the training. Okay, so again, now on the model training, the first thing is going to be to specify the model itself. So we have to say what type of model it is, what engine we're using. So remember, the engine is pretty much what package you're using from INR. For conditional inference tree, I think there were like 4 or 5 packages that could do. So you have 4 or 5 potential engines. For random forest, I think we also have 4 or 5 different packages that can do it. We have to specify which one we want through the engine function. And also the mode. So if you remember, the mode is when you say if this is going to be a regression or a classification problem. Random forest can handle both. It will depend on what type of Y variable you have, what type of response variable you have. In our case, our mode is going to be regression. And then the 3 hyperparameters that we could, we can change more of them, but the 3 that people most commonly tune are tree. So we talked about their overall names in the introduction. Now I'm telling you the specific argument name in the function. So number of trees is called trees. So it's how many trees we allow this forest to have. The number of random features sample age node split is called mtry, and the minimum node size is called min n. I want to tune our model just for the first two for simplicity, but you could tune all three if you wanted, or even a subset of those three. But I would always recommend at least tuning trees and mtry in random forest algorithms. All right, so let's get here in the coding side. This is where one of the places where you're gonna have to code with me. Because again, this is the one of the places in this code where it makes a difference on what algorithm you're training. So that's one of the changes you're gonna have to make with me. All right, so if you just come after that first comment that we're going to specify random forest as our model type and asking to tune some hyperparameters. So the function from parsnip, so parsnip is a package from tidymodels that handles machine learning models. The name of the function is rand_forest. And in here, we specify the model level hyperparameters that we want to tune. So we're going to tune two of them. One is trees. To tell the algorithm that we want to tune it, if you remember, we just say tune. Instead of, if you give a given number here, if I say trees equals to 700, it's just going to run that model. It's not going to tune for us. So the tune is a placeholder to say we want to fine tune this. Give it a comma. The next one is called mtry that we're going to also say to tune. All right, this is our model level. Now give it a pipe. If you come after that second comment, we're going to specify the engine. So here we're going to use the function set_engine. And in quotation marks, we say render. So this is the name of the package that is going to be used behind the scenes to train this model. And then lastly, let's add a pipe, come after the next comment. We're going to specify the mode. So we use a function set_mode, and then in quotation marks, we say regression. One thing for you to remember, when we did elastic net, we fine-tuned two hyperparameters, mixture and penalty. Both of those were specified at this level. So at the level of the model type, which of course it was not rainforest, but it was, I think it was like linreg for linear regression. For conditional inference tree, we had one hyperparameter at the level of the model type and then one at the level of the engine. What that happens when across all engines, if all the hyperparameters available to me are the same, regardless of the engine, then that hyperparameter is going to be specified at the model level. When you have a given hyperparameter that is specific to a given engine, it does not appear on this level, it appears on the engine itself, which is what happened with the conditional inference tree last time. So the minimum criterion was an algorithm that was specific to PartyKit, which was the engine that we used for CIT. And because of that, if I put that on this level, of course, with a different function here, it was not rainforest, it was decision tree. If I put minimum criterion here in that example, it would not work because that is not a hyperparameter that is common to every engine in that model type. In this case here, random forest, trees and mtry are common hyperparameters for all engines. That's why they appear in this level and not at the engine level. All right, so if you just run, this is our random forest specification. So we are saying that's regression. We're going to fine tune mtry and number of trees using the engine render. Awesome. Okay, so for us to do hyperparameter tuning, we're going to need three things. First, our model specification, which is what we created above. We need our recipe, which is also in the weather recipe object. And then we need to set our resampling strategy. One thing I want to call your attention to here is, if you remember on the previous exercise on the conditional inference tree, we had one more line here, which was the model parameters. We had to create that because we had that engine-specific hyperparameter. In this case, we did not have that, so we did not have to create that parameter specification, which is what I'm saying here for your future reference. So to set our resampling strategy is just the same code, right? We have not changed anything. You can just go ahead and run this chunk, making sure you run the set seed so we at least try to get the same results at the end. Where we're just doing a five-fold cross-validation of the training set, right? So now the training set was split in 5 parts, where for each fold here, a different part is used for testing. All the others are used for training. We saw this already in the past, nothing new here. All right, I again want to use iterative search here today, which is the same algorithm as I introduced last time, which is simulated annealing. I'm not going to go through the deep explanation of this again, but just so you remember, we have one hyperparameter in each one of the x and y axis. We start with a point in the first iteration. It's going to then search for a radius around that point of potential new values of that combination of one and the other hyperparameter. Is going to randomly select one of them. If that model is a better model, it keeps that. If it's not the best model, it keeps searching that parameter space until it finds either finds the best model or it reaches the total number of iterations, one of the two. So more details here, which were already in the script from last class, so I'm not going to get into that detail. So here is our, don't run this yet. I want to just tell you the following. The same code as before. The only difference I commented off the param info RF param, because again, we do not have to do that for this case. And the reason for that is we only have model level hyperparameters. There is no engine specific hyperparameters, which if you do have, which was the case of CIT, then you have to create this part of the code. We didn't have in this case, so I just wanted to show you that we're not using that, just cutting it out. All right, I have 50 iterations. I do want to tell you that for random forest, it takes longer to run because again, it's going to be training many models. So many individual models where in each model, there's going to be many trees, right? So imagine that. So we're going to be running, I don't know, potentially like 50 models or no, I don't know how many models going to be in the end, but many models, and each one of those models is an ensemble of potentially 1,000 models. So a lot of things going on behind the scenes. It takes, I don't know, maybe 3 to 4 minutes to run it. I ran with 50 iterations when I did this, and it was able to find a best hyperparameter combination of values at iteration 8. So I want to propose we do 10 iterations and see what happens. Don't forget to set seed and then run that and then watch your console. Because in there is where you're going to see the magic happen. So it's starting with the initial best combination that gives an RMSE of 2.79. And then now it's navigating that parameter space between trees and M-try. And notice how now each one of these lines are taking, I don't know, maybe 5 seconds or so to appear. Whereas with conditional inference tree, they were like boom, 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 pretty fast, right? Now it's taking a while because the model being run behind the scenes is more complex. Yeah.
I got previous code.
You go what?
Error. It's fine. I get much smart stuff. Please.
All right, so at iteration 8, it found the new best combination. And I was telling you that when I ran up until 50 iterations, it did not find anything better than what it found at 8. So that's why we reduced to 10, just so we don't sit here for a long time just watching it not improve. All right, so we
I just have a question.
Yeah.
So I don't think this is a problem, but when it started out the optimizing RMSE, my initial best starting off, yours was 2.79, and mine was a 2.80850. Is that a problem or is that fine that we have slightly different?
I'm not, so were you able to find a new best at iteration 8?
No, sir. Mine said it accepted suboptimal at 8.
Okay, so you're getting different results. I think Sikar is getting different as well from,
Me too.
but what was it able to find a new best for you all?
Yes.
Mine was the first one. It said new best on.
Okay, so I mean that could happen because of different reasons, like depending on the seed, if you're running or not, and how this first step here is found. So for the sake of this exercise here, you know, we're just gonna keep moving. If it was your own research, you would like to have more iterations here, right? So you would go for a longer number of iterations to make sure you find a new best as well.
Thank
Yeah.
you.
Was number 1? Okay, so some people found the best on number 1. Awesome. Well, I mean, this, you know, this is just the training part of the model, right? Which is gonna, it could potentially impact our best value of hyperparameters in the end of the training phase. So at that point, you know, you can decide if you want to use mine, so your results match with mine, or if you want to use yours as well, that's fine as well. We can do that. All right, so if we just print the result here, we have 55 rows. Because we had, let's see, we had 10 iterations. And then, oh, and then it tried, so the remaining there is just a result of how many paths it took, in this case, how many values it iterated over. My gosh, that the word stuff. For our different folds. So that's just a result of that. And if we just pull the metrics of one of those, here's what I see at least for one of those iterations, our MSC of 2.9, R square of 0.11. All right, so I left you the code here for collecting the RMSE and plotting it. I made some modifications to the code compared to the previous time, but you really don't have to worry about it. It's just for visualization purposes. If you run that, this is the path that it took, at least on my side. So it started at 24 trees, just, sorry, M try of 24. So 24 random variables at each split being considered, and just above 500 trees. And then it just walked around the space that we see between M try and trees. And the best value, so this is RMSE, right? So the best value is the lowest, happened right here when he had about 31, maybe 31 trees or something like that, or M try of 31 and about 550 some trees. If I do the same plot for R square, it's going to look very similar, but now the metric is R square. And we see, in this case, we want the highest, right? So highest R square is the better. I see that iteration number 8 for me was the highest because I'm coloring. The points are colored. I guess I forgot to say that. The points are colored according to the metric. So in this case here, the highest is yellow. Highest R square is better. It was on iteration number 8 for me. And in this case here as well, the points were colored according to the metric, but in the first plot was RMSE. So the lowest is the best. I mean, the same pair of M try and trees gave the lowest RMSE and highest R square, but that is not always the case. All right, so today we are going to choose again the best model, but based on a different function than both of the previous exercises. So on the first algorithm for the elastic net, we use the select best, so with the single best model. On the conditional inference tree, we use the select best within one standard error. So again, if you have the best model, you look within one standard error of a given metric of that model. So let's say one standard error of RMSE or R square. Within that group of models, you select the one that was the most parsimonious, or the one that had the least parameters, the least complex model. Today, we're going to be using a different approach, but it has still a similar implication. So if you come here on this chunk, give it a pipe, we're going to use the function select by, and you can see there is a select by one standard error, which is what we used last time. Today, we're going to use the select by percent loss. So we need to specify one of the two hyperparameters for that to look into. I want to specify trees. Then we need to say what metric we're using. On this chunk, the metric is RMSE. So metric equals RMSE. And then finally, it has a different argument that the others did not have, which is called limits. So the default limit is 2. You can change this to anything you want. What this limit means is this is a percent limit of how much you are willing to expand your search. So let's say that within 2% of error of our MSC, I have 3 models. I select the most parsimonious of the 3. If I increase this 2% to 10%, so I'm willing to lose 10% of our MSC, then your list of models are going to increase, and then you choose the most parsimonious. So that, again, the default is 2, but you can make this, I guess, even more strict if you want to have a limit of 1%, or less strict if you increase this number. So if we run this, at least I get a combination of memtry of 24 and trees of 518. Did anyone get a different value at this point? All right. So let's go ahead and do the same, but for R square. So give it a pipe. We're gonna, again, use the select by percent loss function. Again, gonna use the trees parameter. We're gonna say metric now is gonna be equals to RSQ for R square. So that is a difference from the previous chunk. And then limit, I wanna keep that in 2% as well. So if we run that and we print it, it should be the same combination of parameters as for our MSC. So 24 try 518 trees. What are you getting?
1.1.
27.
Yeah, 27. 27, 441.
Okay, so maybe let's do this. If you, okay, so Jonathan, okay, so a lot of people got different. Are your different values the same as what the guy said?
Mine is 31 for any tribe.
Okay.
Trees is 570.
So let's go ahead and you can all use your own, and we can do that. And this is just for R square. So for our MSC, you all got the same.
Yeah.
Okay, so let's use our own R square based parameters. So if yours is different from mine, go ahead and use yours, because I'm curious to see if that's going to impact
I have
other
changed
metrics.
the limit to 3 and it gave me the same answer that.
Okay, so you changed limit to 3 and then it gave the same answer. Interesting. Yeah, I mean, I think we can all keep our own R square specific parameters, and let's see how that goes. So increase to 3 and you still got the same ones that you got the first time. Okay. Mine was different, 27 try 441 trees. Okay, so that's okay. If we're all getting different ones, let's still go ahead and use your own specific that you found, and let's see if that, how much that impacts our test R square and our MSC in the end. So in the code here, I left you most all of it. So we're gonna make our final model specification. So we just rerun the algorithm, but now we set our trees and mtry to the best value coming from the R square metric. I left you, you have to code here on the specify the engine. There's gonna be a little bit of a difference here at this point. So we're gonna set engine just like before. So if we can start typing, set engine. It was Ranger like before. But now this algorithm, the Ranger function from the Ranger package, has this specific argument called importance. So we're gonna say here importance equals to permutation. And we'll talk more about what this means when we get to the importance plots. But if we don't say importance equal permutation, it's not going to calculate variable importance, which it means that when we get to that part of the code, if the code is just not going to work because it didn't calculate for us when we set the model engine. So just this difference here, make sure then you connect with a pipe. So it goes through with the set modes and then go ahead and run this model or this chunk. All right, now we're going to get our last fit using the functional last fit, which does, this is the same as before, but just to remind you, what the last fit does is that it's going to train the optimal hyperparameters that we found on the entire training set. Up until this point, no model that we evaluated saw the whole training set at once. We were doing folds, right? So within each fold, the model was being trained in 4/5 of the data and assessed on 1/5. So no model up until this point saw the whole training set at once. So the last fit's going to train the model on the whole training set and then create predictions based on the test sets. So this is the first time the test set's going to come into play, is when we're evaluating an already trained model. If you run this chunk, the code was the same, so there's nothing to do there. It just gives us, if we collect predictions, it just gives us the predictions that is given us for the individual observations in the test set. Now let's look into the metrics on the test set. And Benita, you were asking about this the last time, so let's evaluate here. So on the test set, I'm getting an RMSE of 2.9 and an R-square of 0.19. How much? 21? Anyone higher? 21? Okay. Yeah, it's still comparable, so I wouldn't worry too much, but it's, yeah, there's some, you know, it's coming, potentially coming from the differences in the hyperparameters. And then itself, you know, has different ways that variability can get into it, but it's still, you know, comparable to some extent. So I think that's okay. Now let's look at the metric. Well, I guess before we look at the metrics on the training set, how does this performance of random forest compares to the two previous models? If you all remember. So for CIT, if you remember, I think we got an R-square of like 0.05, maybe like a 5 or 6%. For elastic net, I think we were at like 13, 14%. And random forest is definitely the best one of all three that we tried. All right, so let's look into the training sets and the metrics there. Look at that. So if you're reading a paper, they're telling you an R-square based on the training set. Wow, that's a great model. 0.95 R-square. So again, this is why if you want to provide your R-square on the training model, just to give an idea of how well it fit the training, great, you can do that. But you should also provide the metrics on the test set and make that distinction, right? So this, what it says here is that our model was able to fit our training data very well. However, if we use this model for prediction, the agreement is a lot lower, right? So always keep this in mind when you write your papers and also when you read papers. Try to understand what type of metrics are they giving you. Is it based on the test set, on the training set? That's important for you to understand how to interpret the quality of that model. All right, so let's do a predicted by observed. So this is, again, one of the most popular plots in machine learning, because regardless of how complex your model is, you can always create a predicted by observed plot. This is how it looks like. So still, if you're within fiber strength of, let's say, between 27 and maybe 33, your prediction, you know, it's not the best, but it's not terrible. It really falls short on the tails of this distribution. So if your observed strength is perhaps less than 27 or maybe more than 33, then your prediction is really farther away from what you would be observing. All right, one last thing here that I want to talk about is variable importance, and we're going to make a plot of it. So in random forest, there's a few ways that we can assess variable importance. One of them is called permutation. So we're also going to see an impurity being another type of metric. I'm not going to show you how to explain to you of what impurity is. If you wanted to get impurity metric, you could just change this argument when we set the engine and we said importance equals permutation. You can get impurity if you do importance equals impurity. But I want to talk more about permutation itself. So the way the permutation works in very general terms is basically taking a variable, looking at every tree and every split that variable was selected. Now taking the values of that variable and shuffle them. And then run through the same model and see how much accuracy you lose when you basically shuffle this column. It's basically saying, so imagine that every other row in the data set is still the same. You're just shuffling the values under this column. You're just permuting the values of this one column that you're assessing importance. If this variable is not important for the model, shuffling the values is not going to change much the difference in accuracy of the model when you have the non-shuffle column and the shuffle column. So again, if the variable is not important or not very important, shuffling the order of the values of just that column will not impact model performance. However, if this column is very important explaining strength, right? So imagine that your strength values are not being shuffled, they're fixed. And this column here is very important. So this association between strength and each one of the values of this column has a very strong correlation. If I come and I just shuffle the X column, so the predictor variable, and of course I'm not shuffling strength, now this relationship gets degraded. Because if this column that I'm shuffling, that I'm permuting, is very important, and I compare the performance of the model with the variable as is and with the variable shuffled, the model after shuffling is going to have a decreased performance because now I kind of broke down that relationship that existed originally between strength and a given weather variable, right? By shuffling the weather variable values in the column. Permutation is doing that for all the variables. So it's looking at which trees and which nodes of the trees across all of the forest use that variable, each single variable. It takes that trees, makes a prediction with that tree only, and then takes the same tree, shuffles that variable, makes a prediction with that shuffle variable, and looks at how far they are from the actual value, observed value. Again, if it was an important variable, important feature, shuffling its values will make your model very weak. And so your prediction comparing on the non-random column with the randomized shuffle column will be very large, the difference in model predictive ability. So that's what permutation is doing behind the scenes for us. I know this can be a little bit abstract. So anyone has any questions that I may be able to help to understand if you're confused? Yeah.
When like the hyperparameter for random forest is 3, right? 3, M try and the mean number of nodes. But when we specify the model, we only specify 3 and M try, but we do specify the mean.
So if we wanted to also train the minimum node size, well, let me ask you this, where do you think that would be? So I guess a good answer for that, for any model would be, let me find our training here, would be right here, right? So there is an argument here called min n. So if I wanted to tune the minimal node size, I would say tune here as well. If you want to do that later, you're welcome to play around with it. I'm not going to do it in class just because it may take more time for us to get through the computational time of the algorithm. But that's where you would change it. So every time you're training a model, and again, and this is something you're going to know just by Googling, right? I don't know these things from the top of my head. Like what are the algorithm what are the hyperparameters of the algorithm? Are they specified at the level of the model type, or are they specified at the engine because they're specific to that engine? Those things I know because I Googled, right? I don't know them from the top of my head. But that's where you would either specify an algorithm that you want to fine tune on the level of the model type or on the level of the engine. Oh, your question is if we don't need.
I agree to that, but I don't know, I didn't get why we didn't. do that.
Gotcha. I thought you were asking where we would do it. Okay. Yeah, so we didn't do here. So I think the default value is 5. So a minimal number of observations a node is 5. I guess, I didn't do that because this is like a secondary type of hyperparameter. So it would perhaps change a little bit your performance, but the main ones are these two, the trees and mtry. So just to keep things simpler, that's why I decided to do. There's really no other good reason. Yeah, I mean, you could definitely, and you probably should do all 3 if you're doing for research. Okay.
Dr. Bastos,
Yeah.
is there any thumb of rule for that how many iterations you should run?
I don't think, I mean, not that I know of.
Like you did for 50, if we do 500 or more, you will have better possibilities or not?
Potentially, right? So so the more iterations you can do, so I guess what I would do when I'm assessing that is kind of looking at this space here. And so in our case, we could argue that we don't have any points falling here, we don't have any points falling there. That could either be because the algorithm understood that those were not the best places to go, and so we avoided. Could be that, or it could have been just random chance as well. So I guess what I would try to do is look at these plots, look at how much of the space your iteration process covered. And maybe if you still think, oh, maybe I want to have a point here, maybe I want to have a few points here, you can come back if you want and do a fixed grid search and put points there and evaluate that way. Either that, or you can increase number of iterations. Increasing number of iterations with random forest is gonna take longer. I mean, depending on the data. So in this case here, I think it was taking me, I don't know, 5 minutes to run 50 iterations or something like that. If you can spare the time, then increasing is probably better, at least until you find a new best. Yeah, so that would be my recommendation, but I don't think there's a good.
To improve your ask and RMC, so like if we know that we have this many mtry, so can we fix and run more iterations near that number?
I believe on the simulated annealing algorithm, I think you can provide a grid to kind of focus there. We didn't do that here, but if you look into the documentation of the function, I believe you can do that. Yeah, that's a great question. Yeah.
Right, because our school value on the training and distancing is different, so use difference. It is normal to have that much, and if that's not the variation. Then that's it.
Yes, let me repeat that for those online. So Jyoti was asking if it is common to have that much of a difference in performance when we look into comparing the test and the training sets. So, that will depend, I guess, on the model type as we've seen. So the difference that we were observing on the previous models were not that large, right? It was, I mean, normally your training metrics will be better than your testing. That is common. In the case of random forest, and that again is one of the reasons why it is one of the most powerful and yet simple algorithms, is that because it has so many trees and each tree is potentially looking to a different relationships within this data set because of the bootstrap and also the mtry being different in each split node, it is able to learn your training set very well. Right, so I mean, this, I guess, I don't know if we would say that this is overfitting. Perhaps we would, I guess, I'm not quite sure, but if you think of it, every time you give a training set to an algorithm, that algorithm is going to try to learn that training set the best, right? And when you bring new data the algorithm has not seen, then you would expect for your performance to degrade because it has not seen that data yet. Now, how much that difference is going to depend on the algorithm type, as we've seen here, is going to depend on the quality of your test and training set as well. So we talked about this before, that if you do a test and training, and by random chance, it happens that all observations in your test are very different from those in your training, that would also cause a large discrepancy here, because you're training, let's say you're training on data from Georgia, and then you're testing on data from Texas, right? So that could be a reason as well. We did not explore that here in this exercise, but that could also be a reason. In this specific case here, I would say is more related to the algorithm itself, because we also ran the same training and test with two other algorithms, and that difference was small, right? Now, random forest, it was really high. So it's probably more related to the algorithm itself than to the testing and training. Yeah, and I mean, when I saw the R-square on the training, I was really impressed. I didn't think it was going to be that large. So, I guess it just shows us how good of a job random forests can do when finding patterns in data that maybe simpler algorithms like ElasticNet and conditional inference tree don't have all the flexibility. Yeah.
Like, as you said, you can, when you split the data from training and testing, if it's randomly select, right? So if you again split the data, then you will have different R-square and maybe have better R-square, because when you split, like you will separate the different.
Yes. So let me repeat that for those online. So Benita is asking if we do a different split, or maybe we use a different, we still do 70-30, but we do a different seed. So different observations fall into training and testing. Could that impact this as well? Yes. So that will most likely impact more algorithms that have higher variance, like for example, conditional inference tree. So if you redo our splits and different observations go into training, different ones go in testing, you may get a different result in the end of the model. So the model in the end that you train may be different. We hope that it wouldn't be that different, but that is also related to the algorithm. So conditional inference tree has high variance. And what that means is that for each different draw of data that you give the algorithm, you could be creating different models in the end. Random forest is less susceptible to that. So even though there may be some differences, but you would still expect, as long as your training and testing have similar distribution of the response variable, especially, you would expect if you train a machine, random forest with one training and test, and then you do another one and you train again, your final model should be more constant. It should be more stable in how well it's doing. So maybe on a CIT, on a conditional inference tree, so we do a 70-30 once, run a model, gets to the end, and you have a given model. You do again your training and testing with a different seed, so get different observations, get to the end, it may be a completely different model. With random forest, it is more stable. So your model in the end would still perform very well, regardless of the different observations going to training or testing. Awesome, great questions. Any other questions?
I have a tangent question. So out of all these three models that we have done, so how would we choose that which one we use? Do we have to run all of them and see which one gives us the best R-square?
That's what we would do. So, so papers that evaluate machine learning algorithms normally do that. They normally, and I think it's interesting when the different models they evaluate have this variability in simpler models that are easy to interpret, but maybe less accurate or have a lower predictability, and more complex models that are very tough to interpret, but have a very powerful model, like a very high predictability, right? So this trade-off between model interpretability and model complexity normally exists. So normally these papers would have, maybe 3 models. Let's say the 3 that we ran is a great example of that. ElasticNet is the simplest one. It's the most interpretable one. Or maybe, I would argue that CIT is more interpretable, but I guess in the context of linear regression, ElasticNet gives you the coefficients. So it's still very interpretable, right? So ElasticNet being the most interpretable, also simplest, and potentially the lowest predictive ability. CIT being intermediate, random forest being the most complex, least interpretable. Although even though in our case, we saw the CIT was the poorest performance, right? But normally people do that so you can discuss around that trade-off, because you may have a model that is very good at predicting, but it's very hard to interpret. And normally in science, we want to interpret things. We want to know what is this model doing that gives me a very good prediction, right? If you're purely in a predictive field, you may not care about it. You may just go with the most complex model. That's the one, if that is the one that gives you the highest R-square. But in our case, normally we want a balance of those 2 things. So that's why you would run many of them and then compare. Okay, so let's see where we were. Yeah, we're talking about permutation. So basically the permutation itself was done when we set the engine of the final model specification, and we asked for it to keep track of the permutation as our variable importance metric. And if we do that, then we're just getting our final spec model, fitting that through the data, and then getting the variable importance in this function, doing some lie wrangling, and then just plotting. So if you run that chunk, it should go through. And this is where we see the variable importance. So we see the 3 top most important variables in this case is the mean solar radiation in August, also the mean solar radiation in June, and the minimum temperature in June as well. So those were the top 3 most important variables. So those were the variables that if you go to your tree and you shuffle those values, what happened if you're getting different ones? Sorry, I saw your eyes going wide. I was like, whoa, something happened. So which variables are you getting on top? Okay. So solar radiation, July. So your top one is solar radiation in July, and then the second one is the same?
No.
Second is mean time, third one is your third.
Okay. Interesting. Well, and the what?
Your first one is out of time.
Okay, so my 4th one is solar radiation in June. Okay,
Yeah,
No.
your first one is third.
my first one is
Just
3rd.
Go to third number.
Gotcha. Okay. Let's see, somebody had a comment. My top one is July also. Okay. Yeah, so we see some variability here. That could be, I'm not quite sure where this is coming from, but with random forest, there's so much room for randomness that is, even though we're setting seed, it's still difficult to fully reproduce. I guess overall, we're still seeing similar variables and at similar times of the year coming up as the most important ones. Maybe by random chance, my solar radiation in August appear more in a tree, in all the trees compared to maybe your solar radiation in June or July, whatever that was. So it could be because of that, right? So there's a lot of randomness behind the scenes, and we're running so many models at once that it could be all related to that. But at least I will, I think we will still be getting a similar interpretation of it. That seems like solar radiation at the peak of summer, maybe minimum temperature at the peak of summer are some of the most important variables here. So at least we'd be interpreting this similarly, even though the specific variables are not the same.
Also, that's would we expect a similar graph with the other two models, like the same variables being important for the other models?
We did do the same plot for the others, right? And I do, like, if we just open those scripts, you would be able to see, I think they're very similar. Yeah. So on the elastic net, we have the importance is based on the coefficient, right? So it's a different way of giving importance. It's just the coefficient of that variable in the linear model. And if I remember well, I think that one of the largest coefficients was solar radiation in September, perhaps. July. Still solar radiation. Yeah. And then in the condition inference tree, I think it was also like solar radiation in September or August or something like that. So it's still similar. I guess what we're learning from the data is similar, even though different algorithms, different ways we're training them. But it doesn't have to be, right? Maybe it could be a case where they're not the same. And that is also part of, understanding the limitations of the algorithms, how you interpret them. Like this is not, we're in the best model, we're explaining about 20%, the R-square is about 20%. So there's still a lot of room for unknown in these models. So we cannot just take one of these models and take that as the universal truth that solar radiation August is always going to be most important, because it may not be, right? As we're seeing just within our class and the same data set, we're getting slightly different results. All right, so very quick summary here. So today we started and finished running the random forest algorithm. We went through some of the theory behind it, how it works, what makes this algorithm very powerful, and one of the most popular across different domains. We set up the workflow to train this model. One of the different things that we did today, so we did an iterative search that we have already done before. That was not new. We did a 5-fold cross-validation on the training set to find the best hyperparameter values. We evaluated the best model using the best within 2% loss of within the number of trees. And looking at R-square in that case, that's the way that we chose our best model. And then we evaluated with different plots as well. Okay, I think before I move further, I just want to ask if you all have any questions. Yeah.
So if we need to run random forest for like classification, then where does the process do for that?
So the question was, if you run for classification, where does it change? So it will change. See. So maybe you may have to change. Well, if you just keep the same results, let's say for this example specifically, if we just had a column that we were using as our predicted variable and that was categorical, you would not have to change anything in the recipe. You would really change here. You just say classification. And well, here and whenever you specify the formula in the recipe, I guess at that point, I didn't make it clear. So on the recipe here, this is where we establish the formula. So in the formula, this variable here on the left side of the tilde is our response variable. So it will have to be a different one. You have to be the column that has that categorical variable, right? So let's say that we had strength class that was low, high, medium. I would have to just change the name of that variable here. And then on the model is just classification. It also changes when you are evaluating the model, because on a classification type of model, we do not have R-square or MSE. We use different metrics. So, if you ever heard of confusion matrix, that would be the type of, well, some of the metrics you can use for a classification model, but there are many others. So the metrics you use to evaluate are different as well. That part would change in the model as well. But as far as training the model, it's just this. You would change this to classification. Awesome. Yep.
Have variables, make numerical and categorical. only we can use gender.
You mean like as X variables? Yeah, so random forest handles that, conditional inference tree also handles that. Um,
If we have mix, maybe
Yeah.
just one X with categorical and others are numerical, we cannot do that.
So again, for random forest and conditional inference tree, you can. For elastic net, you cannot right off the bat, but you can transform them to dummy variables. So you can, but you have another step on the recipe to process that categorical data for the regression part. Yeah, and this again is something that if you go back to that resource I showed, which has many different algorithms and what processing steps each one of them required, there's a column that says dummy. If that dummy is checked for a given model, then you have to do dummy encoding, which is, you can go back to that recipe list and there's a way to do that. Yeah, so if a model, so random forest and conditional inference tree, you don't have to do dummy encoding. For elastic nets, you do. So you can accommodate categorical variables along with numerical variables. I believe in most any algorithm, it's just how you code that. The way that the variables included in the model may be different. Awesome. Any other questions? All right, so I want to share with you some further resources. These are great resources. I was getting a lot of my teaching material on the theory of things from these resources. I do want to share with you. The first one is, so all of these are ebooks that you have online. They're all interactive. It's not like a PDF. You can actually go through and it's a very, very nice way of learning. One of them is Tidy Modeling with R. This is the book that the person, so the name of the person that put together Tidy Models is called Max Kuhn. He's a researcher at our studio. Before he joined our studio, he was the author of the package Carrot, which is a very popular package for machine learning in R. And some of the concepts that he developed for Carrot were things that our studio as a whole wanted to incorporate, but in a more consistent framework. So that's then that our studio hired Max Kuhn to develop Tidy Models, which is based in many concepts of Carrot package, but better. So a lot of really great documentation on this ebook here, Tidy Modeling with R from Max Kuhn. There is a Tidy Modeling with R book club, which is a different resource. It's kind of like an extra added resource that goes along with the first one in case you're looking for more resources. There's this great book here, Hands-on Machine Learning in R. This is perhaps one of my favorites of the list. Has a lot of the topics that we covered and others. And I got a lot of figures from my introductions from this source. And then finally, Machine Learning for Social Scientists, even though it's a different discipline, but it has really great examples of how things work. I do want to say that I was pulling my resources and developing code based on all four of them, and perhaps even more resources that I did not include here. So I don't think you're going to find anything like our code exactly, like simple like our code in any of these single ones. The code that I showed you, I developed based on many resources to try to give you the simplest, most efficient way of doing this. That's just a heads up. And I just wanted to show you here the Hands-on Machine Learning with R ebook. So there's really a lot of great resources, but if you come here, it has, for example, linear regression, which is what we did, logistic regression, regularized regression, which is also what we did, nearest neighbor, decision tree, bagging, random forest, gradient boosting. So this is one that if we have more time, this would be the next exercise we would do in class. So let me just tell you this. In machine learning, so machine learning meaning that we're not doing deep learning. We're not doing like or any type of neural network. So we're still within the machine learning side of things and working mostly with tabular data. So as you start getting into deep learning, people may start using image for image recognition, pattern recognition. You may start using audio, video. So those different types of data, non-structured types of data On machine learning side of, which is what this class was doing, was more on the structured data side. So when you have a data frame that you can give to a model. Within those algorithms, again, the three that we saw are popular. Support vector machine is popular. Gradient boosting is popular as well. It is, so if you've never heard of Kaggle or Kaggle, not sure how to pronounce that, but it's a platform, it's a website that does machine learning competition. So let's say if you're a company, you have a problem, have a data set, and you want someone to find a solution for you, you post it there, you say that the best model that whoever creates gets, I don't know, $50,000, then a lot of people start developing models for that competition. So in Kaggle competitions, for models that remain within the machine learning side of things, gradient boosting is probably the top model, is the model that most frequently was used by the top placing of any competition. So gradient boosting, I would say, if you want to further learn, go for gradient boosting. And sometimes, and just to tell you this, you know, we may have this idea that, well, if I just throw a neural network at any problem, that's always going to be the best solution. That is not correct. There are many situations where gradient boosting, which is not any type of, is not a neural network, can outperform, even random forest can outperform a neural network type of model. It all depends on the model complexity, how many data points you have, how many, you know, correlations and complexities you have within that data. So for example, if you have a small data set, most likely a neural network is not going to be the best model for you because you don't have enough observations to properly train it. However, it may still be a good size for random forest or gradient boosting to do a good job. So just because a model is simpler does not mean it's always going to be lower performance. Simpler models can even outperform more complex models depending on how much data you have and the complexities in that data. Just to keep that in mind. If you want to further learn, I would say gradient boosting is a great one to go further. And then also here it has deep learning, support vector machines, stacked models, which is really interesting, is when you use more than one model to make predictions. We do not see this. Principal component analysis, other things, k-means, hierarchical clustering. So there's a lot of really great stuff here, and they provide the R code for it. So really great resources with great explanations, figures, and all that. I do recommend that you look into it. All right, so we're gonna have a quick quiz, but before that, I want to ask you all: did you get that student evaluation email? Okay, so last year we got that before our last meeting, so that did not happen this year. If you have gotten that email, I would ask you to take 5 minutes in class and respond to that, but it seems like that's not going to be an option. So what I want to ask you all is, whenever you do get that email, that you will get a link. I thought this link here was going to work, but I don't think it does. It does not, right? Yeah, so just ignore that link. It's not working. But whenever you do get an email for student evaluations, I really ask you that you fill that up. That's going to help me tremendously, regardless of what feedback you have. Now, I really want to know how the pace was, you know, with the topics we covered. You know, I know in my head originally, I wanted to have had a little bit more balance between the first part and the second part. It turned out that we were spending more time than I anticipated on the first part, which made us cut on the tail of the second part. I will think about that for next year that I teach this. But you know, I do want you all to provide me your feedback so I can know what went right, what I can improve, and any perceptions you had about the course, and you know, any other feedback is greatly appreciated. So whenever you get the email, please fill that up. It shouldn't take a lot of time, and it's going to be greatly important on my side if you can provide me your thoughts. All right, so now I have a quick quiz for you that's going to serve as your attendance as well. So let me just make that visible. And actually for this quiz, if you have a person next to you, you can pair up. You can answer that in pair. I mean, you have to answer individually, but you can talk with your neighbor, with one of your neighbors, to not all of your neighbors, to come to the answers that you submit. So again, submit individually, but you can talk with one neighbor and discuss what you're going to submit. So I don't think it's active yet. If you just give me a moment. All right, so I think it's visible now. It's just named Quiz Machine Learning Model Comparison. So it has, I think, 3 or 4 questions for you there. Please answer them. If you want to work with one of your neighbors, you're welcome to. And yeah, and make sure you submit both. I mean, all of you submit your answers before you're done for the class.
I find for this look of this.
So that's it. You're running for a specific number of each model there.
Yeah, so I'm looking for the specific number of performance. And just, I guess I'm looking at the questions. I want it on the test set. So performance on the test set, not the training set.
You want test set, but you have written what we trained.
I mean, we trained the model, but I want the performance on the test set.
Thank you for telling me that.
Yeah, I guess I could have been more clear on my question here.